Doesn't matter. I will start. I hope others will join. Okay. Itime is there. Good. Okay. So I hope we can start. So yeah, we are. We'll start with from where we left in the last class. So let me share with you the PowerPoint. Yeah, I hope you can see. You can see this. So the course is thermal physics, and therefore the course is thermal physics. Therefore, in the background, this is the sun. Okay. So how does the sun look here? It looks good. Huh? Okay. So we learned about zeroth law of thermodynamics in the last class. I hope this was clear. Then, okay, today we should start with first law of thermodynamics, okay, and the mechanical equivalent of heat, like those things. Okay. Okay. Zeroth law notes have been given. Okay, but what is thermodynamics? That thing we still have not. What is thermodynamics? We have not yet. Okay, you may write down in your note. Actually, I have uploaded the note in Google Classroom, so you can also take it from there. So it's up to you. You may take the note. So I think you can write it down from the Google Classroom. So let me just discuss what is thermodynamics, what
Okay,
is
sir.
mechanical equivalent of heat, or what is the law of thermodynamics. The notes are there, so I am not going to give you notes. You don't have to write. Okay.
Okay, sir. We
Okay,
will write it from the
thermodynamics,
Google Plus.
by definition, thermodynamics is the science, or in other words, it is the branch of physics which discusses the relation of heat to mechanical work. Okay. It establishes the equivalence between work done and the heat produced. The principles of thermodynamics are very general and give the relationship of heat to other forms of energy, like electrical energy or light energy, etc. Okay. So thermodynamics, in other words, is the branch of physics or branch of science which establishes a relationship of heat and mechanical work. So in this slide, you can see Q is the amount of heat, W is the work done by the system. So this equation, this is the first. This is equation is the equation of first law of thermodynamics, and thus it is establishing a relationship between heat supplied to a system and mechanical work. It will also discuss like how much work from the heat will be. I mean, from heat, how much of the heat will be converted to work. Okay, it establishes the equivalence between work done and heat produced. Okay, so when we will read about second law of thermodynamics, there also we will learn like if you supply a certain quantity of heat to a system, how much of that heat will get converted to work. Okay, and give the relation of heat to other forms of energy. So this heat may be, it may be utilized, it may be of different forms, like electrical energy. Due to electrical energy, also heat is produced. When current flows through a conductor, a heat is produced. Okay, so like that. And similarly, light. No, if you supply light, if you shine light on an object, then what happens? Then also heat is generated on the system. You also know that. Okay, like the sun. No, you can see the sun in the background. So the sun is giving us heat, and heat is also a form of energy. So energy can be of various forms like electrical energy, light energy, etc. And whatever be the law of thermodynamics, be it the second law or first law or second law, so it always discusses a relationship between work and heat. Okay, or it establishes the equivalence between the work done and heat. Okay, so that is more or less the definition of thermodynamics. Okay, so you can find the note in Google Classroom. I have seen that many of you have joined the Google Classroom, and of course if somebody has missed to join the Google Classroom, I think I have given the link today also. You can check the link and join the Google Classroom. Okay. Okay, so we'll come back to the first law of thermodynamics in a while. But there is another concept, thermodynamics we have learned, and then there is something called mechanical equivalent of heat. I mean, how you can mechanically how work and heat are related to each other. Actually, okay, I think I have a slide related to this. Yeah, so I hope you can see this slide, heat and mechanical work. So actually, in your practical course of this semester, there is a no, calendar and Barnes apparatus to for a practical by which you can calculate mechanical equivalent of heat. Mechanical equivalent of heat is nothing but this J quantity, 1 calorie. This thing you have to find, no. So this not 1 point, this 1 calorie is 4.186 joule. So this particular number you have to find, and this is called the mechanical equivalent of heat. So this is also in your practical. So I hope you would have learned this concept much better with your practical. But we have to wait till when the there is power cut. Anyway, so we have to wait till the university is opened and we can start the practical classes. But until then, you just learn about the concept. The concept is called, as you can see here, the name, which is the mechanical equivalent of heat. Okay. Okay. So the definition of it is something like whenever work is transformed into heat or heat into work. Okay, so work, you do some work, some amount of work gets converted to heat, or from the first law you have seen here, it will supply some heat, it may get converted to work. Like here you have seen in the first law of thermodynamics, you are supplying some heat and this heat is getting converted to work. The quantity of work is mechanically equivalent to quantity of heat. So the quantity of work is mechanically equivalent to the quantity of heat. And this relationship is, okay, I will try to annotate here. I hope it works. Okay. I hope I can write here. So it is W is proportional to H. Okay. W is proportional to H. So this work done is proportional to or equivalent to heat, but it is just proportional to, and if we have to establish a mathematical relationship, so you can write this as W is equal to JH, capital J. Okay, my writing is not so good here. Capital J multiplied by H. H is this one, no? So W is equal to JH, capital JH. So J is the quantity. J here is the quantity which is the mechanical equivalent of heat. Okay. And this note I have given already in your Google Classroom today. Earlier today I uploaded it. So you can download and go through the note. Okay. So this is the quantity mechanical equivalent of heat. So what is mechanical equivalent of heat? So you can there are maybe a few definitions of this. So mechanical equivalent of heat is the quantity which connects work done to heat of a mechanical system, or how mechanically heat and work are related to one another. So that is mechanical equivalent of heat. Okay, and J is the generally W equal to JH is the expression by which you can like establish the relationship between work done and heat. Okay. J is a constant known as Joule's mechanical equivalent of heat. Okay. So the value of J is 4.186 joule. So this one is the value of J. I think I can use red color here. So this one is the value of J, 4.186 joule, okay, per calorie. Okay, how joule per calorie? I think I will also show you that. So, okay, anyway, so this is the relationship, joules per calorie in SI unit, but if you go to the CGS unit, it is, 1 joule is 10 to the power 7 arcs per calorie. So in that case, in CGS unit, the mechanical equivalent of heat will be 4.186 multiplied by 10 to the power 7 arcs per calorie. Okay. Okay, so chalta is there. Okay, yeah. Okay, the unit is okay. I'm writing the unit. Unit is uh, joule divided by calorie. So you may think that both joule and calorie are the same units. No, they are the units of heat. Okay. So then, yeah, but because you come to the relationship W equal to JH, and J is the mechanical equivalent of heat. Okay, let me write down here. Okay, this is a border. Okay, this is not any mathematical symbol. So J is equal to W by H. Okay. So W is the work done, H is the heat. So work done unit is joule, and H unit may be calorie. Okay, so it is joules per calorie. Okay, that's why joules per calorie is work done, unit of work done, and therefore it's okay. We have written it here. So this is the unit of mechanical equivalent of heat. And if J equal to 1, if J equal to 1, then when J equal to 1, J is equal to 1. Okay, there is another border here. That means it is different from the previous one. In that case, W is equal to it. Or in other words, how you can define mechanical equivalent of heat? So you can say that mechanical equivalent of heat is unity, or it has a value of 1 when the work done is equivalent to the heat produced. Okay, so in that case, J, the quantity which is mechanical equivalent of heat, that is 1. Okay. Okay, so that is more or less what is heat and mechanical work. So mechanical equivalent of heat. But again, when we are studying about or reading about thermodynamics, so this relationship between work and heat will evolve. So it will evolve once with the first law of thermodynamics, and the next time it will evolve with the uh, second law of thermodynamics. Okay, I have removed this annotations. Otherwise, it was looking a bit dirty here. Okay. Okay, then after mechanical equivalent of heat is not given in your syllabus, but I have included because it is there in your practical. Okay. Okay, now let us come to the first law of thermodynamics. So, first law of thermodynamics, again, I am going back to the previous slide, which also I think we discussed earlier, earlier in the last class. So, what is the first law of thermodynamics? Okay, so from the note which I have given you, you can access the note in Google Classroom. So, I am just reading it and then I will explain it to you. Okay. Okay, the how we can write it. So whenever heat is imparted to a body, okay. So you have given heat to a body. A part of it is used to increase its internal energy. So okay, let me again write down here. Okay, again go back to annotation. Okay. Okay, so from this equation, so Q is okay. Maybe I change the color. Q is equal to delta U plus W. Okay, so okay, this is Q. Okay, you should not miss it. This is Q. Okay, let me read again. Whenever heat is imparted to a body, so Q is the heat which is added to a system or imparted to a body. A part of it is used to increase its internal energy. A part of the heat is used to increase its internal energy, which is given by delta U, same quantity here. That is, increase in internal energy means increase in which quantity? Temperature. Increase in internal energy means increase in temperature. So when you are supplying heat to a system, that particular heat is increasing the temperature of the system. Okay. uh, increases internal energy, that is to raise its temperature. Increasing internal energy is raising its temperature, and the rest in doing external work. Okay, can I write text here? uh, Text. Okay, so so maybe you can follow. Let me see. Okay, I have to change the color of the text to maybe red here. uh, so increase in internal energy is equal to raise in temperature. Okay, you are increasing internal energy of the system, which is equal to raise in temperature, which is nothing but this quantity. Delta U is the raise in temperature. Okay, and the other part delta W, which is the quantity. Sorry, only W, this quantity. These two equations are same, so don't get confused with these two equations. So W is the quantity which is the doing external work by the system. So again I'm changing external work by the system. Okay. So is this equation clear to you or not? So the equation says you are supplying heat. Okay, maybe I write something more here. Heat supplied. Heat supplied. Heat supplied, that is used in increasing internal energy, and that is okay, I cannot choose this. and the other part is doing external work by the system. Okay, heat supplied increase in internal energy and in doing external work by the system. So this is the this is the statement or the definition of first law of thermodynamics. So you see, we have just learned the definition of thermodynamics. So it establishes a relationship or it establishes an equivalence between heat and work done. So heat is here, Q is the heat and W is the work done. So this equation is also a, I mean, this, that is why this is the first of thermodynamics. Okay, or this equation satisfies the definition of thermodynamics. In other words, okay, in other words, this first law of thermodynamics or the first equation of thermodynamics satisfies the definition of thermodynamics. Okay. Then I have written in the note, which is more or less similar as this one. If delta Q is the heat energy absorbed by a system, heat absorbed by a system is, as it is the same thing. You have supplied an amount of heat delta U to the delta Q. You remember these nomenclatures. Okay, Q is for the heat, U is for internal energy, and W is for the work done. So here in the note I have written, if delta U is the increase in internal energy, okay, and delta W is the external work by it, then provided all the quantities are measured in units of work, the first equation of thermodynamics is first law of thermodynamics in equation form is delta Q is equal to delta U plus delta W. Okay, and then I have written this equation is known as the first law of thermodynamics. So this is the same thing which you are here in the note which I have provided to you in Google Classroom. This also says the same thing, but there they have used this quantity delta. So yeah, okay. So this delta. So this delta. I hope you understand this delta. And how here also they use the delta symbol, but it's okay, delta or change. The the purpose of using the delta symbols is to the is to indicate the change, no, the change. Okay, so I hope have you understood this first law of thermodynamics. The definition is also written here. So this definition also you can use whatever is given here in this note. You have seen the change in internal energy of a system is equal to heat added to the system minus the work done by the system. So if you think that you want to write this definition, yes, you are free to do so. You can write this particular definition also for first law of thermodynamics. Okay. Okay, so definition we have learned, and okay, so next question is, what is the significance of this first law of thermodynamics? I mean, we have just learned it by definition, but if you were asked, like, what does it even signify? Okay, okay, so the note has been given to you, and yeah, you can follow it from there also. So this equation is nothing but, if you see this equation carefully, this equation is nothing but it represents the law of conservation of energy. Okay, so energy is conserved, like you are supplying uh, a quantity of heat to a system, and that heat gets conserved gets utilized in increasing the temperature of the system. Increasing the temperature of the system means increase in internal energy, this quantity, and the system itself will end up in doing a work. Okay, so this one. the system itself ends up in doing a work. Therefore, the quantity of heat which you have supplied is completely utilized. Okay, and that means what? Whatever heat added, heat is equal to heat utilized. Okay, and so there is conservation of energy, like initial amount of heat or energy. So heat is also a form of energy, you know. So initial amount of heat or energy is utilized in doing two different things. One thing is change in internal energy, and the other thing is in doing work by the system. Okay, so this equation signifies the law of conservation of energy. Okay, so whatever we have written here, physical in physical significance part, physical significance of first law of thermodynamics. The first law of thermodynamics is simply the conservation of energy principle. So you can see this equation gives us the conservation of energy principle. So you all know by now what is the conservation of energy principle. So heat can neither be destroyed nor be created, but it changes from one form to another, and this is the case here. Okay, so yeah, so it recognizes transfer of energy through either work or heat, and it includes internal energy of the system, all forms of which includes all forms of energy and represents kinetic energy. Okay, so it includes heat supply. Okay, so it requires transfer of energy through either work or heat. So you are supplying heat, so energy is transferred either in the form of heat here, or either in the form of work given here. Okay, and also it involves internal energy. So internal energy expression is this one, and internal energy, increase in internal energy means increase in temperature. If your temperature is constant, that means there is no change in internal energy, or in other words, if internal energy change is zero, that means there would be no rise or no increase in temperature. Okay, so but again the question arises, maybe I have also discussed with you in the previous class. The question arises is what does this internal energy term include? Okay, internal energy term includes, I have also mentioned in the note given to you, all forms of energy like kinetic energy and potential energy. No? So we know internal energy. Okay, can I write somewhere? Okay, not with red ink, but with a light ink so that you can see. So internal energy is equal to Ke, okay, Ke plus Pe, kinetic energy plus potential energy. Okay, so kinetic energy is like no the molecules or atoms of the system. So when you are supplying heat to a system, so the atoms and molecules no they begin to vibrate, no, and they get some velocity of motion, or they even move sometimes. So in case of metals, you know, the electrons, anyway, so that way they get kinetic energy. Okay, and potential energy means so there is a position, no, position of atoms and molecules in a substance, and from the definition of potential energy, it is the energy due to configuration and position of a system. So the atoms and molecules, they are already present in any given system, so they have potential energy. But when you are supplying heat to the system, they get motion sometimes, and due to this motion or due to this vibration or whatever you say, they get velocity, and this velocity gives rise to kinetic energy. Okay, so that is the this thing, that is the that gives rise to uh, total internal energy. So total internal energy is yeah, kinetic energy plus potential energy of the system. So these are the three quantities which are involved in the first law of thermodynamics. So first law of thermodynamics, one of the significances is it gives it is nothing but a form of conservation of energy, or it tells us about the law of conservation of energy, which all of you know very well. It recognizes the transfer of heat through work sorry transfer of energy due to either due to work or due to heat, and also it involves the quantity internal energy. Okay, so all these three quantities are involved. Okay. Then we have written this law establishes the relation between heat and work. Yeah, of course, this first law of thermodynamics establishes a relation between work and heat, as you can see in this equation. This is the heat, this is the work. Here also, this is the heat, this is the work. Okay, so that is what thermodynamics does. Thermodynamics generally establishes a relationship between heat and work. Okay, according to this law, then what we have written, heat can be produced only by expenditure of energy in some form or the other. So heat can be produced by expenditure of energy. Okay. So so expenditure of energy means you supply heat. You supply heat. Yeah, internal energy increases. So internal energy increase means like temperature rises. Okay. So that means you are supplying some form of energy. The heat temperature rises means it also gets heated. So this heat, energy, temperature, so they are interrelated with one another. That is the thing, and which is signified by this first law of thermodynamics. Okay, that is also one of the significances of first law of thermodynamics, because it in general establishes a relationship between energy, work, and heat. Okay. Hence, next line what we have written, hence it follows directly from this law that it is impossible to make a machine without expenditure of energy. So what does it mean? It is impossible to make a machine without expenditure of energy. So why machine thing comes here? Because machines, what do machines do? Machines do work. Okay. So you see this quantity is the work. Okay. So machines do work, but will machines just do work by itself? Huh? So where is Raihan? So Raihan, can you tell me, can a machine do work by itself?
Yes, sir.
Can machines do work by itself?
Yeah. No,
So
sir. We need to like put energy. We need to
so
put energy.
yeah,
Then only.
so for all of you, not only for him, but for all of you. So this quantity work done would not exist without Q or without delta Q. Here also same equation, don't get confused. Okay, these are the just two different forms of first law of thermodynamics. Don't get confused. You can write this. If you write this in exam, I will give you full marks. If you write this in exam, I will give you full marks. So don't worry about that. My question is, this work done, is this quantity possible without Q? Q is energy. The answer is no. Work done is not possible. In order to get work done by a system, there must be heat. Okay. So it is impossible to make a machine without any expenditure of energy. And as we will move to like second laws of thermodynamics, and then we will learn about Carnot cycle, Carnot engine. So I think these things will get more clearer to you. So these are some of the significances. So first significance, law of conservation of energy. Second significance, it establishes a relationship between work, energy, and internal energy. And another important significance is that uh, in order to get work done, there must be some form of energy available. If there is some form of energy, then only work can be done. Okay. Okay, but that we have been talking about first law of thermodynamics, right? But is it like defect free? Okay, so let me stop the annotation so that I can go to next slide. Okay, so limitations of first law. So is the first law of thermodynamics defect free? That means is it perfect? No, it is not perfect. So it also has some limitations. So what are the limitations? So I have given you some. I have given you in sentences, two, three. So okay, what I have written you. Let me just explain, and then I will explain the points given in this slide. Okay. This law, however, does not specify the condition under which a body can use its energy to produce a supply of work, nor does it say how much of heat energy of the body can be converted into useful work. Okay, so again, it does not specify the condition under which body can use its heat energy. Okay, under which condition a body will use the heat energy, or how much of the heat supplied will get converted to energy. Okay, so anyway, so here the points are I think quite well written, so let me read. So it can give the direction of proceed or direction of proceed, okay, transfer of heat from hot body to cold body. Okay, so maybe in one of the earlier classes we have already discussed that heat always flow from a hot body to a cold body. Okay, but heat does not flow from cold body to hot body. Okay, so it is always the hot body to cold body until both the bodies become equal at temperature. Okay, that is more or less the zeroth law of thermodynamics. Now they will achieve thermal equilibrium. Thermal equilibrium means again they will have the same temperature. Okay, so but first law, from first law of thermodynamics, it is not clear whether heat will flow from a hot body to a cold body or from a cold body to the hot body. Does it say so? Does first law of thermodynamics say so? No. The first law of thermodynamics does not say this. It only says that if you supply heat, some portion of heat will get converted to work and some portion will be used up in increasing the internal energy. Okay. So it does not say the direction of flow of heat. I mean, in which direction heat will flow? It will flow from hot body to cold body or cold body to hot body. Although we all know that heat always flows from hot body to cold body. Okay, and when we will learn about second law of thermodynamics, we will learn about this. Okay, so second law of thermodynamics addresses this particular limitation of first law of thermodynamics. Okay, so so all processes involved in conversion of heat into work or vice versa are not equivalent. Okay, so uh, uh, okay, the meeting will end in 5 minutes, so in 2 3 minutes we'll finish. Okay, so all processes involved in conversion of, so this like unlike in second law of thermodynamics, when we learn about the Carnot cycle, in Carnot cycle you will learn about all the processes, okay, like isothermal process, adiabatic process. But in first law of thermodynamics we do not know about the which process, the processes involved. in which work gets converted to heat or heat gets converted to work. So this thing will be clear when we learn about a Carnot cycle in second law of thermodynamics. Okay. So amount of heat converted into work and vice versa. So this is a very important point. So how much amount of heat will get converted to work, okay, and vice versa, or how much work will get converted to heat. So this is not clear from the first law of thermodynamics, okay, but it can be done from, say, it can be understood from second law of thermodynamics. So another thing, um, insufficient condition for process to occur. So under which condition will this conversion of heat to work will occur, okay. So that condition is also not clear. There may be some condition for for heat to get converted to work, but that is not clear from the first law of thermodynamics. Okay, so these are some of the limitations. So it cannot tell us about the direction, like from hot body to cold body to hot body. All processes, so like under which process the heat will get converted to work. Is it adiabatic, or is it isothermal, or it is some other process? Now, how much amount of heat you get converted to work, or work gets converted to heat? That is also not clear. And insufficient condition for process to occur. So, under which condition this things will occur? Okay. This is also given in the note which I shared with you, so you can also read from there. But this is also quite good. Okay. So this PowerPoint I will share with you at the last. Okay, so that maybe at the end of Unit 1, so that you can summarize all of what we have learned. Okay. Okay. So I think I am going to end here because we don't have much time. And okay. Okay. So I have. Okay. I am stopping the share. And I am also stopping the recorded video. So thank you. I'm stopping the recorded video. Okay.
Ah, may hod.